Sir, we may start now. Okay.
Okay,
So,
sure.
they are joining. Uh, Good afternoon, participants. So welcome for the third session of the day. So in this session, we have Dr. Arup Kumar Pal. So on behalf of the Department of Computer Science and Engineering, it is my privilege and pleasure to welcome Dr. Arup Kumar Pal, Associate Professor, Department of Computer Science and Engineering, Indian Institute of Technology, Dhanbad, to deliver expert talk on DNA-inspired data compression and image encryption. Dr. Pal is currently working as an assistant professor, associate professor in the same department. Before joining this institute, he was a lecturer in the Department of Computer Science and Engineering, NIT Jamshedpur, during April to December 2011. He received his BTech in Computer Science and Engineering from Government College of Engineering and Textile Technology, Berhampur, India, in 2006. He did his PhD in Computer Science and Engineering from IIT ISM Dhanbad in 2011. He has more than 9 years of teaching and research experience. He has contributed over 70 research papers in several international reputed journal and conference proceedings. His main research interest includes data compression, multimedia security, and CBIR. He has organized several FDP in the area of image processing and cryptography. He has served as an advisor committee member and technical program committee member in various conferences and workshops. His research articles are well recognized by the eminent scientists and researchers throughout the globe, and that achieves till today 984 citations, having H index 18 and I10 index 28. So welcome, sir. Welcome for spending your valuable time with us. I hope this session will be very interactive to the participants. So I invite you to deliver your lecture. So over to you, sir.
Okay, thank you, Professor Sangram, and good afternoon to all of participants. So let's start my today's lecture. Now, is it visible to all of you?
Yes, sir. It's
okay,
visible.
Okay, so today basically discuss about the DNA-inspired data compression and image encryption process. Okay, now why you are discussing these two topics? Actually, whenever you talk about the image encryption process, so generally think about the compressed data, because as you know that the image data is basically huge and in volume. So they are basically highly correlated. So that means whenever you want to perform any kind of operation on image data, so naturally basically think about the compressed data. So that's why I thought that it is better to club together that two topics, that is the data compression, and with respect what way we can extend these things with respect to the image encryption process. So first of all, we discuss about the DNA-based data storage. Okay, so that is the one of the new hot topics in this particular research community. And here the DNA. So if you see the growth of the data, so you can see this particular chart. If you see this particular chart, you can see here that growth of the data is exponentially increasing. And as per the data, of IDC, the data will reach around 175 gigabyte by 2025. And hopefully every person can keep more than 500 GB data in their coming days. So in this aspect, what happens? So we need some kind of new technology to store the huge volume of data. Okay. So conventional storage devices like a magnetic tapes, hard drives, cloud storage are insufficient because they require lots of physical space and volumes. So we need some kind of different technology. Okay, so because earlier what happened, we started with the 1 GB pen drive, but today's scenario you can use the 64 GB or like this. So that means the storage capacity is huge. Even we believe that we need some different kind of technology to store this volume of data, the huge volume of data. Now, how the DNA plays the important role? Now, DNA is basically, I'm not the biologist, even I can share some brief about the DNA. The DNA stands for deoxyribonucleic acid, and it having the three base nitrogen is nucleotides. The nucleotides are adenine, cyanine, and guanine, and the thymine. And the thing is that AT, they are basically complement, means AT and GC. A is complemented T and G complemented C. And basis on that, they basically form. So that means if there is a, so definitely it will be T here. If there is a G, so definitely there will be C here. So this is the complementary, they basically form this hexagonal structure, they basically form. Now, in these regards, now what is the DNA? Now, DNA says that if we can theoretically says that a 1 gram DNA can store 455 hexabyte of data. Just to see here, 1 gram of DNA can store 455 hexabytes of data. So that means somehow we can, the DNA dust you can store in a test tube, and that test tube can store, if it is a test tube contain the 1 gram of DNA, so it means that you are storing basically 455 hexabytes of data. And 1 exabyte is basically 10 to the power 30 GB. Another advantage is that if you store the data in the form of a DNA, that DNA basically is stored in a long period of times. It is not like that if you store in a magnetic phase, so there is a chances that your data will be lost. But in such a case, if you store the content in the form of a DNA dust, so that basically stored in a long duration. So error rate is very less in this particular process. Now, actually, what way the DNA is computing basically works. Now, suppose you have a data, that your data you capture through different kind of image capturing devices, like you can use camera, mobile phones, all those things. So basically, you are storing, you are capturing this binary data. Okay. Now, this binary data will be encoded into the DNA sequence. So DNA sequence is ATGC. ATGC is basically are the DNA sequence. So that means we basically encode this particular binary sequence into DNA sequence. Now, here up to we people have your control. Up to this means once you capture the data, you just convert the data into DNA sequence. Now, in this particular black box, it basically performs the synthesis. That is the chemical reaction. So that means it basically performs the chemical reaction and it produces the DNA dust. And that DNA dust you can preserve it. So that means once the DNA dust will be stored, so that means this particular DNA dust is stored, keep it with you. If suppose you need this particular thing, so again you read this DNA. There is a DNA sequence reader is there, and after you can read the DNA, then you convert the DNA again the DNA sequence, and again from the DNA sequence you convert into binary sequence. Okay, so this particular process is very having huge cost. So still now this is having the huge cost. So that means we people are basically thinking that is a very compute, but the thing is that somehow we can create the 1 gram DNA dust So that can store the huge volume of data. So that is the very one of the advantage. Okay. So whatever is the cost, that is not the main concern. The main concern is that if you can somehow can create a 1 gram of dust, the dust can store in a long period of times and it can store a huge volume of data. Okay. As a computer scientist, we people have some role in this particular encoding process. Okay. So that things we want to say because we have a no control in this particular things. We have a no idea about this, what is the way this particular process. But the thing is that that particular performance is having the high computation, high cost, and that cost can be minimized if we can choose some efficient encoding process in this particular cases. So as a computer scientist, I can talk about in this particular reason. So is it clear how the DNA basically works? DNA computing?
Yes, sir.
Okay, thank you. So in this particular process, is it visible? Hello?
Yes, sir.
Okay. So in this particular process, you have a different phases. You have a digital data, then you basically encode the data, then you perform the DNA coding, and then you perform the DNA synthesis. DNA synthesis is basically the construction of DNA dust. You just realize this is nothing but the form to form the DNA dust. And that dust will be stored, and again you can perform the DNA recovery process, and finally you get the information of this DNA data. Now, in this particular process, we have a two constant. That means the biological, chemical biological operation basically happen with the two constants. The constants are GC constant and run length constant. GC stands for guanine and cytosine, so GC constant. So what is the GC constant? The number of G and C nucleotides in a DNA sequence must be nearly half of the total of the entire DNA sequence. This ensures lower sequencing error rates and easier to synthesize. To perform the efficient synthesis means the DNA sequence will be converted to DNA dust. In that case, if the GC constant is around 50%, then we can say that is efficiently you can perform the DNA synthesis process. Am I clear? So GC constant play an important role. So that means whenever you design any coding algorithm, so that means in this particular process what happens? So this is your binary data, and this binary data will be encoded into DNA codes. So here this particular, once you encode this particular DNA codes, here the number of GC, that is the number of GC should be 50% of the total number of sequence. Okay, so that is the one of the constant. If it is preserved, then synthesis will be properly done in this particular process. So synthesis one of the main condition is that GC should be 50%. Second is the run length constant. Run length constant, what is this means? Run length is the repetition of same nucleotides consecutively. A DNA sequence having long run length cause both sequencing and synthesis problem. Okay, so say for example, suppose you have a consecutive G. So here you can say the run length is basically 3. Or you can say that you have a 2C, consecutive 2C, where you can see the run length is 2. Okay. Now, as per the DNA synthesis process, your run length should be maximum 3. And if it is 1, then we can say it is a more stable. Okay. So that means whenever you convert any binary to DNA, so that means you should preserve the GC constant should be 50% and run length should be at most 3. So at most 3 should be the run length, and if it is a 1, then it is quite stable in this particular process. Okay. So basis on this assumption, so that means in a DNA coding, the GC constant percent should be around 40 to 55%, and run length constant should be maximum 3, and if it is better, if it is close to 1. Okay, so we basically, we as a computer scientist, we basically try to design some algorithm that convert the binary sequence into DNA sequence, where the DNA sequence having the GC constant should be the 50%, and run length constant should be the maximum 3. Problem statement is clear? Is it clear? Hello? Okay.
Yes, sir.
Okay. So,
Sir, I have a question.
yeah. Tell me.
So GC constant 15% means AT is also 15%.
Total combination will be the ATGC, and total number of GC should be the 50% of total sequence.
Okay, sir.
Okay, and GSC basically occurred in a complement way. Yes or no?
Okay, sir.
That I have shown you this particular diagram. यहाँ पर देखिए, that is adenine thymines, that is yellow and green, complement way.
Yes, sir.
Yes or no? Now, what is the cost? The cost of a synthesis DNA lies around these billions as per this data. Synthesize, storage and resolution requires considerable amount of time. Okay, so we basically think about the encoding process from binary to DNA encoding process. So this is some literature survey. That is one of the pioneer paper is the Crutch Grove Causary implementation, and this is the pioneer work on the DNA data storage. So what are the way they have converted? They converted the data into 8-bit ASCII. Okay, so convert the data into 8-bit ASCII and replace 0 with A or C and 1 with G or T. Okay, so if there is a 0, that may be A or it may be C, and if it is 1, it may be G or T. Now, what is the advantage? It basically maintains the run length of 3, maintains GC constant to some extent. So this is their advantage. The run length is maximum 3, and also their algorithm basically maintains the GC constant. Now, what is the disadvantage? Low compression. So that is the pioneer work of the Crutch. Now, there is another algorithm, that is Goldman et al. And their algorithm basically consider this way. That means if the current is A, if next is C, then we will encode as a 0. If it is next is T, we will encode as a 1. If it is G, we will encode as a 2. In this way. So they basically consider these things. So they maintain the run length constant with the run length of at most 1, gives better compression, but does not contain the GC constant, but does not maintain the GC constant. So that is their limitation. Okay, so here they are able to maintain the run length is 1, but they are unable to maintain the GC constant here. Now another algorithm, that is the Grass et al. In their particular algorithms, they basically introduce Reed-Solomon code. So Reed-Solomon is one of the error correcting codes, and basis on they have done. So they have basically introduced the error correcting in a way. They basically preserve the run length constant of at most 2, but they does not guarantee to preserve the GC constant. So this is the limitation of the Grass et al. Now another work is the Edlich. So here the thing is that this is their algorithm. So in this particular algorithm, they basically granted the run length constant and GC constant, and the net is quite high, but robust against the dropouts are religious. So this is the summary of the some few base paper of this particular area. Okay, so here they preserve the GC constant, yes, and Goldman and Grass does not preserve, no, and it is also preserved, yes. Code rate is 1, it is close to 2, and robustness, no, it is yes. Error correcting, no, it is having yes. Full recovery, no, and the preserve the run length constant, yes. So it basically preserves the run length constant, but in these two cases, it does not preserve the GC constant. Now, here we basically propose one algorithm that basically encode the binary data into DNA sequence, where we are able to preserve the GC constant is around 50% and the run length is 1. That is our advantage. In earlier algorithm, some cases it is 1 and 2, but in our cases we are able to preserve the run length is 1 as well as the GC constant is 50%. Okay. So this is one of the algorithm that I want to present in this particular lecture series. So here we basically used minimum variance Hoffman tree. Okay, so let's see this particular algorithm. So here our motivation is that to reduce the cost of synthesis, try to more data is less number of nucleotides. That is our objective. Okay, so here we did some Hoffman codes, and I hope you know the Hoffman codes. This is the example of a Hoffman codes. Suppose you have a source SYNOMU, and this is the probability of this particular source. And what happened? We basically consider the least two elements. So first of all, you combine M and U, that is 0.2, and subsequently we will combine that is 0.2 and 0.2 this one, and this way just combined it, and finally you get the tree where the that node having the probability, this is 1. So if you follow this particular path, we can represent the S is 0, 0, Y is 0, 1, and N is 1, 0, and like this. And it is called the prefix code, the prefix free code. That means none of the code word is prefixed to any other. So what is the advantage if you are using the prefix code? The first advantage is that if you are using the prefix code, so that means the code length should be the variable. And if the code length is variable, then you can effectively use this particular code, then the decoding can be effectively carried out in this particular process. Now here we basically use the minimum variance Hoffman tree. So what is the minimum variance Hoffman tree? Now here the thing is that what is the algorithm of the Hoffman tree? The Hoffman tree algorithm is that you take two list element, combine it, and again you take the another two list elements. So when you combine these two, that is 0.1 and 0.2, you have a 0.2. Now in the coming iterations, you have a several 0.2. So next iteration you have a several things. Now the thing is that if you combine this and this, so again you have a 0.4. Next you will combine this and this, again you have a 0.4. And next you may combine these two, again you have a 0.6. And then if you can combine this, then it will be works in this particular manner. That means you took two list elements and combined it, and this continue this process. Now here if you follow this particular process, so here now here what happened, instead of in this particular example, what happened? So if you combine this and this, so it will be 0.2. Now instead of combining this and this, instead of combining this and this, what happened? We have basically combined these two. And if you continue this process, that means it is 0.4. Okay. And again, if you combine these two, again it will be 0.4. And then you combine the next in this particular manner. So here it is combined like this, 0.2. That is 0.1, 0.2, then 0.2, 0.2, 0.4, 0.2, 0.2, 0.4, and then 0.2, 0.4, 0.6, and now 0.4 and 0.6 is 1. And here the variance is very less. Okay, So it is quite balanced compared to this one. Minimum variance if less, that means the tree is quite balanced. Okay, so that is the first advantage. If the tree is having the minimum variance, that means the particular tree is balanced, because Hoffman tree is not a unique tree. It basically produces the different kind of trees possible, and that is the selection of proper the minimum weight of the node. But if you compute the minimum variance tree, it is said that it is quite balanced in this particular process. Now, in our algorithms, we have tried to maintain the run length code that is at most 1, and GC constant should be 50%. And we know that Hoffman code are compact codes, and Hoffman code are the previous codes. So that's why this is our algorithm. So what happened? We have taken the input data, we have converted the data into binary data. We know that we have taken the input as an image, and that image is converted into, we know that the image is basically represented by pixels. Then each pixels will be represented by bits, and again bits will be converted into different planes. Now, what happened here? The bits are encoded based on the minimum variance Hoffman tree, and accordingly you have encoded this particular ATGC, means DNA data are created based on this particular tree. Now, here the DNA sequence is there. Here you have the synthesis process will come, and the thing is that here this particular sequence is quite effective, and it can maintain the GC constant is 50% and run constant is 1. So this is the algorithm how to process this particular process. So here, what is the logic here? Now, suppose your binary data is there, so ATGC. So what happened? I have created tree ATGC like this, and also I created another complement. So suppose any length does not preserve the GC constant, I basically switch that another tree. Okay, so if you follow AG, so there it basically preserve the run length. If it is not preserving, so I basically switch this particular tree. So that means I created one complement tree of our best original DNA tree. So this is the algorithm, and basis on this algorithm, I want to show you. This algorithm maintains the run length at most 1. And here this particular algorithm also preserve, this is the GC constant. We basically preserve this much GC constant. So this is the results of this particular algorithms. Suppose you have taken the block length is 2 by 2, and then your code rate is 1 by 1. So bits per nitrogen component. So bits per DNA component. So that is bits 1. It is 3. And if you take the block level at 20, so you are having more. And this one. So if we compare these things, so most of the cases, that is the in generally we have considered this one. So this just says that we are giving the better compared to the ND. So that ND is basically so the maximum code rate, but here we can achieve the maximum code rates if you increase the number of block length in this particular process. So here. So this is some algorithms. This is the results which are compared with respect to others, different kind of data sets, and we also achieve the comparable results with the existing one. Now, what is the conclusions in this particular one? In this proposed algorithm, minimum variance Hoffman tree has been used for generating DNA sequence to store text and image data. The algorithm gives a high code rate of DNA sequence and therefore reduces the synthesizing cost. It interleaves the compression and variable and constant coding, unlike most of the existing algorithms that are based on fixed length coding. So what is the future scope in this particular area? These techniques can be further extended to video, other multimedia data. Moreover, error detection and correction can be implemented in a DNA sequence to make them more robust. So it means during the time of construction of DNA codes, if you can also incorporate the error correcting and mechanism there, and then it makes more effective for the long run. Okay. So, is it clear? Any questions? Is it fine? This is the one of our paper that was published in the IEEE Communication Letters. So if you search it, then you will get it, this paper. That was published by IEEE Communication Letters. I already told that mathematically we have proved that our that one theorem already proved through the theorem that we can maintain the GC constant is 1, and GC constant is 50%, and maximum random we can prove at maximum at most 1. And this particular area, so many people have shown that if the GC constant is 1, GC constant is 50% and run length is maximum 1, then synthesis is quite balanced. That was not verified by us, that was proved by the research community. Okay. Okay. Still continue the name.
Sir,
Bolo.
I have a question.
Yeah.
So what is actually getting, what is the compression ratio you are getting by this method? Means how much compression you are getting actually?
Compression, the thing is that actually here we have basically, you have misunderstand this particular things. We have basically represented one nitrates by the how many bits. Okay, so ATGC on an average, if you take the block length is 2, so I can represent one ATGC component by 1 bit on an average. Okay, so it means that if you can represent the lesser number of ATGC component, so definitely your synthesized process will be computation cost will be less, and it is the meaningless if you that means if a DNA sequence is more, finally you get the DNA dust. So DNA dust key storing is not the main constant from our end. Am I clear to you? Am I clear or not? What do you mean by the actually compression means what we see here? We see that suppose we are using the JPEG compression. The JPEG compression, basically you have seen that you have a compressed data and you have an original data. If you divide this, that will give the compression. That is the meaning, you know. Yes or no? Yes or no?
Yes, sir. Yes,
yes. But here, what is our objective? Our objective is that you have a binary data. I want to convert into ATGC sequence. That is called the DNA coding. Now, the thing is that if you have a lesser number of ATGC component, so definitely your synthesis cost will be reduced. Yes or no?
Yes, sir. Yes, sir. It's okay.
Yes or no? So that means if you lesser, so here that means you will not get the direct compression ratio. Will basically represent by the code rate. That means how many bits is required to represent each ATGC component. If you take the block of size 4x4, so there we have observed that it can require 1.20 bits to represent each DNA component. It's okay?
Thank you, sir. Thank you, sir.
Actually, I already told you that as a computer scientist, this is the actual process. That image was taken from the EMBL European Bioinformatics Institute. So actually, this is the actual process. That means you have a data, you have this ATGC. So most of the mathematician and computer scientists are basically working in this particular area. The mathematician and computer science people basically working in this particular area. Some people are also introducing some error correcting code in this particular case. Yes or no? Now, this is the part of the biologist. They basically part of the chemical reaction. So binarily you will get the DNA dust, and that dust you can store it. Yes or no? Like a quantum computing. Quantum computing, everything can you run in a quantum computing? It is not like that. Some algorithms run in a quantum computing, some is run the classical computing. Yes or no?
Yes, sir. Yes, sir.
Yes or no? So that means you can think about that it is a chemical reaction that was done by this particular black box, and rest of the things you can do in the classical computers. But here, whatever is the outcome, that outcome you can store in a effective way and in a long duration. That is the objective. Yes or no? Okay.
Sir,
So,
I have a question.
yeah, tell me.
In the DNA double helical structure, so A is always complemented by T and G is always complemented by C. So how can the run length be ever be greater than 1? Because after every A, there should be a T that bridges between the two helical structures.
Actually, the thing is that that should not be, that is the biological way. But here you are getting this binary data. So how can you ensure that it will be preserved all in the DNA sequence? Your statement is correct. But if I keep all are 0, 0, 0, 0, then what happened? Suppose this is your input data. Then what happened? Is it clear now?
So here, let's say we encode one as A or G.
That means
Yeah.
our intention will be to encode these things in terms of a biological property.
Yes, sir. Yes, sir.
Yes or no?
Yes, sir.
When your statement is giving the answer. So our challenge is here. Suppose this is input, because here we don't have any control. Your information can be any way, any kind of representation. So our role is here. How to? That's why I'm telling you. That means your conversion from binary to DNA, and there we should preserve the GC should be 50%, and run length should be at most the 3. Now I think is it clear? No?
Yes, sir. Yes, sir. Thank you.
Thank you. Thank you. Now DNA-based image encryption process. So why need the multimedia encryption means image encryption in a separate way? Because there is already that there is so many standard data encryption algorithm is there, like IDEA, AES, all those things, and we know that those standard encryption are highly secure. Why you study that thing in a different way? The thing is that the image data is quite image or video. So, for example, if you see the video value is so huge, so you need to think about some different way. So, the image data is very huge, volume is very large, and the thing is that the image data is quite highly correlated. So, these things I can show you. This is one of the image. This particular image is the one of the original image. And this image was encrypted by AES directly, and you are getting such kind of outcome. What is the reason? The reason is that image is highly correlated, so same blocks are mapping to the same blocks. Yes or no?
Yes, sir.
Now, definitely you can say that, sorry, why you consider these things? We can use the different kind of block cipher mode, but the block cipher mode have several limitation. That means parallel you can't execute at a time. Yes or no? Because if you are using the cipher blockchaining, so that means previous input is required to encipher the things, because these are the huge volume. Suppose this image size is 512 by 512. So what is the typical volume? 512 into 512 into 8. This much is the typical volume of this particular image. And at a time, your AES can process how many bits? At a time, it processes basically 128 bits. Yes or no? So if you want to process this particular image using the AES in a parallel architecture, so it is not suitable. Parallel architecture is suitable, but that in different block ciphers is not that much effective way you can end these things. And even the thing is that we no need to encipher all the bit in that way. Because actually they basically give the homogeneous reason is there. So if I can break this homogeneity, and then it will serve my purpose. Okay, so that's why encryption images or video with standard data cipher directly is time consuming and not suitable for real-time application. In images, pixels are highly correlated and visually percepts in encrypted image should be removed as well. So here we basically realize the image encryption in this particular way. That is the data stream encryption, multimedia scrambling, multimedia wavelet perturbation. Multimedia scrambling means you just shuffle the content, that is also fulfill the data. Suppose if I say THE, if you shuffle the content, EHT, so definitely you will say that's what is the meaning of this particular message. But suppose if I say, if I provide on image, the image pixels are like this, 18, 12, 36, 240, like this. Suppose your image pixels are like this. And if we suppose this image pixels, like suppose if I say it is a 36, suppose it is a 36, it is a 12, it is a 240, it is a 18. So can you guess this particular from this particular sequence, from this particular sequence? No, it is very difficult and it is not required. Yes or no? But if I say, if I provide EHT, then you can easily guess that actually the original message was TH. So that's why the data encryption is required in this particular text data. But here the multimedia data, if you shuffle the content of these things, even you are unable to guess this particular things actual content. Okay, so multimedia scrambling is one of the way, but it is not recommended because as per the perfect secrecy, that means your data should be uniform distribution after the enciphering. So that's why we need some kind of confusion diffusion architecture. To that I'll explain later. So multimedia scrambling is one of the way. Data stream encryption, that is not preferable. Wave perturbation. Wave perturbation means sometimes what happens, we basically use the different kind of transformation like a discrete cosine transform, DWT. So what is the role of this kind of transformation? These kinds of transformation basically represent your signal into significantly basically classify the signal into two components, that is a significant and insignificant component. In generally what happens, insignificant component is basically discard, and as for achieving the compression, and significant component will basically preserve. So in that particular case, sometimes some algorithm we have seen that they basically use the discrete cosine transform. They have basically changed the coefficient, not the magnitude, coefficient sign. Some cases the coefficient is minus, they are make it plus. And as a consequence, if you perform the inverse discrete cosine transform, so definitely you'll not reveal the actual content. So that's why they have done this kind of algorithm. Some reversible cellular automata they have used. Bit plane based image encryption, that means image are realized into different kind of bit planes, and they basically perform, now they have considered that particular bit is 120 bit at a time, and they have performed the encryption based on some standard encryption algorithm. We people basically likes chaos based image encryption algorithm. What is the chaos based encryption algorithm? Now, among these algorithms, the chaos-based encryption algorithms have become the compelling way of image encryption because of the attractive properties chaotic maps such as erodics, complexity, and sensitivity. And they also show good secure performance and low computation cost. Okay, so these are some examples of the chaotic maps. This is the logistic maps. This is the sign map, 1D infinite collapse maps, logistic service maps, 2D chaotic maps, 2D Hannon maps. So this is the difference. So what is the property? And here the chaotic maps, suppose you are considering the logistic map. In the logistic maps, so initially this is X is the initial value, and here this particular called the initial value, and based on that you will get the next value. So suppose here X0 is given, this one is given, so based on that you will get the X1. And once you know the value, then you can compute the X2. And once you know the value, then you can compute the X3. And subsequently, you are able to compute all the values here. Okay. So here the thing is that if you change this initial parameter, that is called the seed value, your sequence will be drastically changed. So in this kind of algorithms, what happened? We basically consider seed is as a cryptographic key. So here the seed is basically considered as a cryptographic key. And based on this initial key, we basically create our digit size of key, and that key will be used for the enciphering process. Okay, so these are some well-known chaotic maps. There is several kind of mathematical proof is there. Now the thing is that in a conventional encryption algorithm, we have a plain image. We basically shuffle the content, and finally we substitute the content by some simple kind of substitution operation, and finally you will get this cipher image. So that means this particular process will be iterated several times, and finally this particular process will be iterated several times, and again this particular. So suppose if we have a T1 times, and if it is a T2 times, so overall T1 into T2 times it will execute to finally you get the cipher image. That is the conventional way. So this is one of the examples. That is the design 2D infinite collapse map for image encryption. They have taken the image. They have taken these chaotic maps. They are confused and they are diffused, and they basically execute this particular 2 rounds. So finally they obtain the ciphertext. Now DNA-based encryption. What happened? Again, we will use this Watson-Crick complement rules. And there we are using, they basically use this kind of standard encoding rules, that is 0, 1, 2, 3, and rule 1, rule 2. So that means if it is a 0, that is called the fixed length coding. That is called the fixed length coding. And my previous example is basically the variable length coding, but here it is a fixed length coding. Now in this particular case, what happened? 0, 1, 2, 3, A, T, G, C. So here you see that AT and GC. So write down A and T is preserved as it is position. You just interchange the GC. Now C and G is interchanged. AT is present in the same position. So this is the complementary it will preserve. So that means if it is 0, I can, if I suppose they're using the rule 1, I can encode by A. If your value is 3, I can encode is 2. So what is the way? Now suppose you have a 8-bit of data. So 8-bit of data, suppose you have a 1, 0, 1, 1, 0, 0, 1, 1. So in this particular case, suppose you are using the rule number, 1, 0, 1, 1, 0, 0, 1, 0. Suppose you are using the rule number 2. So 1, 0 stands for, that is 1, 0 stands for this one. This is 0, 0. This is 0, 1, this is 1, 0, and this is 1, 1. So 1, 0 stands for, you are using the rule number T, we can represent this is the C. If it is 1, 1, I can consider as a T. If it is 0, 0, I can consider as A. And if it is a 1, 0, that is, you are basically using C. So that means this particular data, if you will be encoded by the rule number 2, CTAC. So this is the way we basically perform the encoding. This is the decoding process. So if you know the C, so if you are using the rule number 2, so that means it will be 2 like this. If you are using T, your decoded value will be 3. 3 means 1, 1 like this. So this is some examples. They have taken the plain image, they have considered the rule 1 to 8, and basis on they have performed the encoding process, and the choice of rule is done based on this particular sequence, and accordingly they are getting this count outcome. Now in our example, we tried to encipher the medical images. Now medical images, what happened here? The medical images have a lower entropy than natural images, because that two images you can see very, keep you see too closely, so here have a lower entropy compared to this one. So we need some more, we have to think about more closely about the medical data whenever you want to encipher this kind of data. So here we basically devise one crypto system that is suitable for the medical images using the DNA planes. So what is the algorithms? Now here in this particular algorithm, you have taken a plane image, and initially we have done some, we have taken the constant parameter that is called the marks, and basis on that marks we have done the XOR operation, and we have obtained this kind of intermediate one initial data. This is basically keyless. There is no cryptography, but in the subsequent stages we have seen that if we use this kind of things, so it will basically enhance the security of your crypto system. Now in our algorithms, we have done the masking, we have taken the confusion based on several iterations, but the diffusion is carried out only once. In a conventional diffusion, kitna hota na? Diffusion is basically done by this again another times, but here we have dropped this diffusion. Even we can show our results, we can achieve our result comparable to all the existing literature results. So we have basically dropped. So there, what is the modification here? We have dropped the one diffusion, that means single diffusion is there, but confusion is there. And here we have introduced one masking process, and in this way they basically use. So that means you have taken the marks, you have confused using the annual cat map, and here we have modified the annual cat map, and later we have obtained the DNA plane, and that DNA plane was enciphered by one logistic map based key scheduling algorithm. So that means initially you have taken the key is 256 bits. That is another advantage. If you take the one conventional data like text data, so every 128 bit you record the 128 key. Suppose you are using the AES algorithm. But here the 256 bit is sufficient to such kind of enciphering to such kind of large images. Now here what happened? We are taken this DNA plane. So that means here we have proposed one key scheduling algorithm also. So main contribution is here. There is a key scheduling algorithm. Here we have dropped one iteration, and according to DNA plane of concept, we are able to obtain such kind of cipher images. So this is the some algorithms, and this is the annual cap property. That means if you iterate these things, you will get such kind. If you this is the algorithm of our algorithms. So we have taken the bit plane, we have encoded, and DNA pitch, DNA place encoded based on 1/4x4 non-overlapping blocks, and then we have taken a 2D logistic map, and here we have obtained this DNA plane one, and finally the DNA is decoded, and we have obtained the cipher image. Okay. One thing I want to add it. Suppose if we drop these things. So what happened? Suppose if we drop these things, then what happens? Suppose if you drop these particular things, so your final outcome is basically is nothing but the DNA in a DNA sequence. So that means if you're, but that DNA sequence in a, not in a proper order, that was changes. So that means if you don't know the actual reverse order, so you will not get the actual message. So that means if you keep this particular content up to this, that DNA sequence, if you can synthesize, so then you get the DNA dust. So that means even the dust can store the message, even that message is in an encrypted form. So that is the advantage. But we people have to show the performance, so that's why we basically decode the DNA sequence to show the results. But actually the advantage is that if you use the DNA sequence here, and up to this if you stop here, so that means your DNA sequence will be the ultimate outcome, and you just further process the DNA sequence based on the synthesized process, and then you get the DNA dust, and you just store it. So that means your data will be stored in a long duration in an encrypted form. So that is the advantage. Okay. But however, we'll show you how much our DNA, this particular algorithm is secure. So this is the results. This is the CT scans of 256 by 256 dimension. This is the 512 by 512 dimension. Now, key sensitivity. What does key sensitivity means? If you change the single bit, so what will be the changes of your original content? And ideally, it should be the 50%. And in our cases, we have achieved around 49 point this much with respect to this particular key. So that is the one of the advantage. And even if you see the histogram of this one is this one, and here all the histogram are uniformly distributed. देखिए यहाँ पर peak है black, maximum black है इसलिए peak है. And here all the components are uniform distributed. Since it is a uniform distribution, so naturally there is a high chance it is close to 8. Entropy will be close to 8. This is histogram analysis. That means whenever you want to design any crypto system, and that cipher image should produce the histogram should be uniform distributed. If it is not a uniform distribution, then cryptographic aspect, that particular algorithm is not a secure one. And that is the correlation analysis. Original image having this much correlation, that's why they are highly correlated. But if you compute the correlation in encrypted image, you will get such kind of relation. So every pixel having correlation will be removed in this kind of algorithms. And here the correlation should be close to 0. This is the results. Here we achieved correlation that is quite close to 0. NPCR, UACR. NPCR is the number of changing pixel rate and unified average rate. And basis on these things, it is close. It should be close to 100. NPCR should be statistically it is observed that this should be 99.5%, and USL should be close to this one. And we have achieved these things also. It is very difficult to achieve this kind of values. Oscillation attacks. Oscillation attacks mean क्या होता है ना? Suppose you have this image, you have ciphered, but due to some problem in your network traffic, your data is lost. Suppose this data is lost, and you know your key. Even the particular key can decode this particular thing also. So that means it can overcome the oscillation attacks also. Noise attacks. Suppose you have an image, and due to the presence of, because the particular content is going through some channels, so that due to the presence of noise in the channels, suppose there is a noise is added, even the presence of noise, you will get such kind of, not exact image, but close to that. Means somehow you can recognize this particular image also. So this particular algorithm can also overcome the noise attack. So this is the different kind of